You guys already know about the architect of the atom. The atom has the protons and the neutrons at the center. Remember that the protons and the neutrons are responsible for mass. Protons plus neutrons equals the mass of an atom or an element. So these are called atomic mass unit. If you look at carbon, it's got 6 protons. If you look at carbon 12, that's why it's called carbon 12 versus carbon 14. That's the mass right there. 6 protons plus 6 neutrons equals 12. Okay, this right here has 6 protons plus 8 neutrons. That's why it's 14. Remember that the proton count is responsible for the identity of the atom. You change the number of protons, you change the identity of the atom or the element. You change 6 to 7, you don't have carbon anymore, you have nitrogen. And then remember that the extent by which the electrons are found in the orbital determines the atomic radius. So the more electrons you have in an atom, the bigger that atom tends to be, except when you go across the periodic table. And that'll be clear when we talk about, um, when we finish today's discussion. But in general, what happens is that these electrons are found in these orbitals. These orbitals are sort of complex. You can think of the orbitals as like a hotel, okay? And that the different floors represents the energy level. And as you go up this hotel, the number of types of rooms are going to be more complex. Like in the first level, you only have one type of room, say the suite. And the second level, you have two types of room, the suite and the penthouse. And within the penthouse, there's like 3 bedrooms, the PX, the PY, and the PZ. And then on the third floor, you might have an S, a P, and a D. You have a suite, a penthouse, and say dormitories. And the dormitories have 5 types of bedrooms, and these bedrooms are labeled DXY, DXZ, DYZ, DX squared minus Y squared, and DZ squared. So you can see that the further out we go, the more spacious the energy level, the more suborbitals that you can fit in. And then, of course, these suborbitals have different types of orbitals. Anyway, that's sort of a summary of what we talked about last time. And today we're going to look at some of the properties based on the interaction between the nucleus, neutrons and protons, and the electrons, and what happens in terms of the periodic table. So this is Dmitry Mendeleev, and Dmitry Mendeleev was a Russian scientist who started to think about the elements that make up the universe, and he recognized that certain elements had very similar properties. And because they had very similar properties, he figured that maybe he could arrange it in a table. And he actually arranged the properties based on the table. And where there was no element that fit the pattern, he put a blank there. And later on, when people recognized or discovered that element, they recognized that it fit Mendeleev's table. And so he is given credit as the father of the periodic table. So he proposed, he didn't discover, because you can't discover something that's theoretical or something put to mind, but he was the founder of the periodic table. And he was the one that was sort of given credit on that. There was another German scientist called Mayer, who also had an idea about the periodic table, but it's Mendeleev right here who's given credit. So this is the periodic table as we know it. And again, I remind you about the properties. You can get a lot of lot of information on the periodic table. If you look at these right here at the very top, that tells you the valence electrons. When you look across, these are called period. It tells you um, how many shells the elements in that particular series, and the series goes from left to right, how many shells maximum for the ground state. Remember, the ground state is where the electrons usually reside. Also remember that an atom, even as simple as the hydrogen atom, even though its ground state electrons are found in the first shell, it's got infinite number of orbitals out there. And so that electron could be excited to those higher energy state, but it always wants to come down to the ground state. By the way, when you take an electron and you can remove it completely from that atom, it's called ionization. And the reason why it's called ionization is because um, the atom now has one less electron, it becomes an ion. So the atom goes from an atom to an ion. An ion's any charged species, remember. It could be charged in terms of the, um, the fact that it has more electrons or less electrons. You can only remove or add electrons to an atom as soon as you start to change the number of protons, which is the other subatomic particle responsible for the charge, because it's the protons to electrons imbalance that causes the charge. But as soon as you remove the protons, which you can't do unless you do nuclear chemistry, you change the element. So really, when in terms of ionization, you're only dealing with electrons. Anyway, going back over here, you can see the different properties of the different elements based on where it's situated in the periodic table. The series is called across is called the period. The series down is called a group or family. And then we have the lanthanide series down here. And this actually fits right in here. It's called the lanthanide series because um, between lanthium and hafnium, you actually jump from lanthium to cerium. And then you go across 14, and then you go back to hafnium, HF. And that's why it's called the lanthanide series, because that's where it breaks off from the periodic table. If you actually want to stretch the periodic table so that it's much more wider, these guys actually fit in between. Just like the transition metal fits between these two columns, well, the lanthanide elements and the actinide elements fit right in here. Anyway, let me go ahead and clear this. So think of the periodic table as a map of the building block of the universe. If you take a look at a map of California, you will know that at the very west, you've got the Pacific Ocean. If you look at east, you got the Sierra Nevadas. If you go south, you get to Baja and San Diego. If you go north, you get to the northwestern states like Oregon and Washington. Well, if you think in terms of that, then what we have is the map of the building block of elements. If you go to the top or north of the periodic table, you come up to smaller atoms. And the reason why they're smaller atoms is because they have less electrons, they have less shells basically that are occupied. And because they have less shell that are occupied, the extent by which the electrons are span out is going to be smaller. Down, you've got larger atoms. To the left, you've got atoms that tends to give up their electron with greater ease. Why? Because over here, it's got one valence electron. If it can get rid of one valence electron, it has the same number of electrons as helium. And so why not give it up? Because then you have the same number of electrons as a noble gas. So because they want to give up their electrons with greater ease, we say that they have better metallic character. Metallic character is distinguished by the fact that elements wants to give up electrons. That's why metals are such good conductor of electricity, because the electrons can easily jump from one uh, metal atom to another, and so the electron flow goes through. If we go ease, what happens is that we have elements that want to gain electrons. And that's because they're missing a few more electrons to get to a noble gas. Remember the name of the game, and you'll see that in Lewis structure, is that atoms wants to give up, gain, or share electrons so that they have the same number of atoms as a noble gas. They have the same number of electrons as a noble gas. And by doing so, they form very stable chemicals, very stable molecules. So again, um, you can think of the trend in that sense: larger atoms to the bottom, smaller atoms to the top. To the left, you've got elements that want to give up electrons. To the right, you've got elements that want to gain electrons. Let me extend this discussion further. As you go down, you notice that the atoms are going to be larger, and that's because the electrons are going to be further out. And remember that the electrons are tied into that atom because of the proton to the electron attraction. Opposites attract. So you would think that the larger the atom, the further out the electrons are, the easier it is to remove that electron. And so we would say that going down, we have a lower ionization energy. Ionization energy is just the energy required to remove that electron so that you get an ion. That makes sense, right? Because the further out an electron is, the less tightly it's tethered to the nucleus, and so it can easily be loosened. On the other hand, for very small atoms, where the electrons are very close, they're going to have that very strong attraction to the nucleus, the proton, and so it's much more difficult to remove that electrons. And so we say that smaller atoms at the top of the periodic table will have very high ionization energy. So you can actually think in terms of the size of an atom and the energy required to remove that electron, or the energy gain when an electron is given to that atom. That's called atomic affinity. Okay, atomic affinity. So we're going to look at ionization energy. And atomic affinity. So sorry, not atomic. I don't know what I'm saying. Electron affinity. Electron affinity. Those are the two concepts that we're going to discuss in this discussion right here. Again, this is a map of the periodic table. Is your S block. This is your D block. Down here is your F block, the lanthanide series. And this is your P block. And again, the block is based on the fact that the very last electrons are going into the p orbital, the d orbital, the s orbital, or the f orbital. Okay. Here's a summary of what I just talked to you guys about. Non-metals, noble gas. Noble gas are right here. This is the halogen. This is the chalcogens. That's the oxygen family. Okay. Alkali is right here. We covered this back in the early chapter. Alkaline is right here. The transition metals are right here. These are called transition metals. And then the lanthanide series is in the bottom. Let's take a look at atomic radius. And here you can see that in terms of, it's exactly what we said. When you go down the periodic table, the atoms become larger. Okay. When you go up the periodic table, the atoms become smaller. The reason, again, is because the shells are going to be more towards the bottom of the periodic table. Elements towards the bottom have greater number of shells that are occupied by electron. What probably is interesting is look across. As you go across why does the atomic radius decrease? Okay, why is it that the atoms become smaller? You're actually putting more electrons, but you're putting this more electrons in the same shell. Okay, so what's happening is that, say you have the nucleus and you have the first shell, the second shell, and the third shell. And let's take a look at the third shell. When you go from, say, sodium to manganese, you're putting electrons still on that third shell. So you're not increasing the shell, new shells by which electrons are fitting. So that size should remain constant. But remember as well that as we add electrons, we're also adding the number of adding protons. And so as we go across the periodic table, sure, we have electrons that are increasing in the same shell again, but we also increase the number of protons in the nucleus. And you can think of the protons as a magnetic field attraction. It's going to pull these electrons closer in. And so you would expect that if you got a greater number of protons in the nucleus, it's going to collapse. It's going to attract those electrons to a tighter degree. And that's exactly what's going on here. We're increasing the number of protons. And as we increase the number of protons, because the electrons are all in the same shell, they're going to be attracted to a greater degree. And that's why you see, as we march across, this is another perspective. This is another perspective that the atom becomes smaller. There are some deviation, of course. You can see, like right here, these atoms go from smaller and then gets a little bit bigger and then they go smaller again. And that's based on the fact of the electron configuration. But that's a difference. You guys will hear about that in a greater detail in Chem 200. Again, here's the radius trend, and in this particular case, you can see that the increasing radius is to the left, decreasing radius is to the right. Here's a better pictorial view of the size of the atom and their atomic numbers. Okay, these are the atomic number right here. And you can certainly see the trend here. Let me show you this video. And again, I apologize for the fact that you can't hear the audio in my iPad for some reason. So I'm gonna pause this real quick and then I'll show you the video on my computer so that you guys can see this. This is Atomic Radius movie, and let me bring it over here. Let me share the screen on that, and then you guys can watch.
It is possible to estimate the radii of atoms in characteristic bonding situations by observing the distances between atoms in molecules. In any given group of the periodic table, for example, group 6A, the atomic radius increases as we move downward. As we move from left to right in any row, the atomic radius generally tends towards smaller values. This occurs because the effective nuclear charge acting on the outermost electrons is increasing. As we proceed across the first long row of the table, in which electrons are being added to the valence shell d orbitals of the metals, we see an overall decrease in radius as a result of increasing effective nuclear charge.
So hopefully you saw that movie in terms of the atomic radius. And again, it says that it decreases because of the effective nuclear charge. Effective nuclear charge is the charge that the electrons, they're all in the outside. Remember, the size of the atom is governed by the valence electrons. How far they are across, how far they are from the nucleus determines the size. But if the electrons in the valence shell, because that determines the size, are attracted to a bigger proton charge, it's called the effective nuclear charge, then it's going to collapse that electron cloud. I don't like to use the word density because density implies that these things have a fixed volume, and they don't have a fixed volume. You're looking at density in terms of mass over volume. You're looking at just the size in terms of each element. And you're going to see that it's simply that the size of an atom, the size of these they're called atomic radius, is based on something called Z effective, which you guys will cover in more details when you get to Chem 200. So let me go ahead and get back to my PowerPoint and then show you, change that real quick here. Okay, so, okay. And here is what's going on in terms of that. Also, remember that, well, I'll talk about that shortly. Next is called ionization energy. Ionization energy. So you can think of the fact that if the electrons are further out, it's easier to remove those electrons. If the electrons are closer in, it's more difficult to remove those electrons. And that's exactly what you see right here. You can see that these height tells you the ionization energy. This is the scale right here. Okay. And so you can see that the smaller atoms generally for a family are going to have the higher ionization energy. So these are the values for the ionization energy in this particular table. And in general, again, you can see that the elements at the very top are going to have higher energy than elements in the very bottom. Then if you go across, because the atoms are smaller, the ionization energy is going to be higher to the right side than is to the left side. Pay close attention to the fact that as we go left to right, as we go east in the periodic table, we just said that the ionization energy is going to increase. And yet, if you look at the difference between nitrogen and oxygen, the ionization energy actually decrease instead of increase. And the reason why that's the case, and you see those anomalies throughout the periodic table, is let's take a look at the electron configuration of nitrogen. Nitrogen has 2 electrons in the s orbital, 2 electrons, this is the first shell, this is the second shell, 2 electrons in the 2s orbital, and then 1, 2, 3 electrons in the 2p. So this is the 2p orbitals, okay? Px, Py, Pz. This is oxygen right here. Oxygen is going to be the off-bar of nitrogen, except now it has this electron configuration. It's got 1 more extra electron. You can see that when we remove an electron, remember we're talking about ionization energy. And it's the energy required to remove the electrons. And the electrons that you are going to easily remove are the ones in the valence shell. You're never going to remove the electrons in the inner core, that is these electrons down here, before the electrons in the valence shell. Why? Because these things are closer to the nucleus. They're going to have a greater attraction to the nucleus. You're not going to ionize them. You're going to ionize the electrons that are loosely held, and that's in the valence shell. Look what happens when we remove this electron right here. Remove this electron right here, so it's now the nitrogen becomes ionized. It becomes a positive. Remember, you remove a negative charge, then there's more protons than electrons, and so that makes the atom a cation. You break the fact that originally this p orbital was completely half filled. When something is half filled, you give the atom added stability. So that's why it's very difficult to remove that electron from nitrogen, because then you break the half-filled shell. Look what happens when you remove the electron from oxygen. You have to remove this right here, not one of these, because then you would violate Hund's rule. You have to remove this right here. It becomes oxygen plus. But by removing that, first of all, it's easier to remove that because the fact that these two electrons are in the same orbital means that they have electron-electron repulsion already. Remember, like charges are going to repel each other. So in that sense, that electron will have a lower ionization energy because it's already being repelled by its near neighbor. Then the other thing that you want to notice is that by removing that, the electron configuration of the oxygen plus is now the same as nitrogen atom. It's half full. And again, you get added stability when the the orbitals are half filled. And so that's why, let's go back over here, the ionization energy for oxygen is much lower than the ionization energy of nitrogen. Okay. And you can see that in different places throughout the periodic table where they have that type of anomaly. So again, this is a blow up, and this is again what we have in terms of ionization energy. It's always the valence electrons that are removing, and this is the trend. As we go from hydrogen to helium, it goes up. That's because we're going across the periodic table. As we go from lithium, this is going across the periodic table again. Lithium to neon, it goes up. Look what happens as we go down the periodic table. Hydrogen, lithium, sodium, potassium, and rubidium are all in the same family. As you go down the periodic table, you notice that the atoms become larger. That means it's less energy to remove that electron because it's further out, and that's the trend that you see right here. Clear that. See, there's a question. There's a question here. It says, I believe that the bigger difference in density is when you go down the table due to the more protons and neutrons. Yeah, you can think about it that way. Also in the chat room, when you move to the right, it gets more compact in volume. Yes, denser. Yes, it becomes more compact because the electrons are squashing the electron cloud. Okay, it's compressing the probability of finding the electrons closer in. So again, this is the trend on the ionization energy. Let's watch this movie real quick. And let me show you that movie in my screen. That's the ionization energy movie right here. And I'll share that screen with you guys. I think it's this right here.
The first ionization energy is the energy required to completely remove an electron from a neutral atom. Ionization energy generally decreases as we move down a group. Because the outermost electrons are increasingly distant from the nucleus, less energy is required to completely remove the first one. As we move from left to right in a given row, the ionization energy increases dramatically because of increasing effective nuclear charge. Notice the periodic character of the change in ionization energy as we move across each row. As we move across the first transition element series, the ionization energies increase slowly in proceeding toward the right. The same trend of increasing ionization energy across the transition series is observed in the second long row, consistent with the periodic character of this property.
So that was a short video clip, and you find that in the PowerPoint if you need to review it in more detail. So let me go ahead and change that screen real quick. Okay, close that movie, and then let's do this. So let's take a look at electron affinity. Electron affinity is the energy gain or loss when an electron is added to an atom. So here's the electron, because generally electron energy is released. And remember, when energy is released in terms of a chemical reaction, it's called exothermic reaction. And if energy is released, then we say delta H, the heat is negative or the energy is negative, meaning that the system is going to lose energy. So that's why you see negative values right here, because electron affinity generally are exothermic process. So don't think of the negative as meaning that it's less. Think of the negative as being gives off more energy, because it's going to have a more favorable, more negative equals more favorable electron affinity. Okay, so here you can see that these elements right here are the most negative, and because these elements want to gain more and have the same number of electrons as a noble gas. Okay, so it's much more favorable relative to these others. And then if you look at the noble gas, they don't have an electron affinity, because you can't add another electrons to the noble gas because they don't want them. They're already happy campers in terms of their electron configuration. Okay, so let's take a look at this movie in terms of the electron affinity, and then you guys can see the trend for this. So let me go ahead and put it up on my screen and share that with you guys. And then start the movie.
Electron affinity is the energy change that occurs when an electron is added to a gaseous atom or ion. For example, when an electron is added to a neutral gaseous fluorine atom, 349 kilojoules per mole is released. In the case of chlorine and the other halogen elements, addition of an electron to the neutral atom is an exothermic process. Addition of an electron to the neutral oxygen atom is also an exothermic process. However, addition of a second electron to form the oxide ion is an endothermic process. This means that work must be done to force an electron onto the singly charged ion to form the oxide ion, O2-.
So again, understand the concept of electron affinity. Electron affinity has to do with the fact that you're adding an electron to either a neutral atom or a charged atom. So you have different degrees of electron affinity. You have the first electron affinity, second electron affinity. You also have something called first ionization energy and second ionization energy. The first ionization energy is removing the first electron from a neutral atom. The second ionization energy is removing the second electron from that ion now that had its first electron removed. So you're removing a second electron from a -1 species. You could imagine that the second ionization energy is always higher than the first. And then if you're breaking up an electron configuration that looks like a noble gas, that ionization energy is through the roof. Okay, it's so much exponentially higher. In fact, it's so difficult, you probably can't do it unless you really concentrate the energy. So anyway, that's the trends that we're looking at in terms of the periodic table. We're looking at atomic radius, we're looking at ionization energy, we're looking at electron affinity. Okay, so the rest here just gives you resource. This particular slide gives you very good summary of what we just talked about. The trends on the periodic table, from left to right, generally it increases. I always say generally because there are always exceptions. Okay, ionization increase. Left to right, it's more favorable towards the right. Those elements want to gain electrons to a greater degree than elements to the left. In terms of atomic radius, the smallest ones are to the top, the biggest ones are towards the bottom. In terms of metallic character, which is the degree by which the electrons are removed, metallic character and ionization energy actually go hand in hand. The greater the metallic character, the lower the ionization energy. Okay, so that is a summary of the elements in the periodic table. So, and we're done there. Okay, we're sort of done here. The next topic that we're going to be covering is structures. And this topic is important because, first of all, it could be very visual, but it explains so much as to why the shape of chemicals are so important. But to understand the shape of chemicals, you first need to know how the atoms come together and in what ratio. You guys already have an idea of what ratio they come together based on the fact that they want to have the same number of electrons as a noble gas. But how about molecules like carbon dioxide, CO2? Carbon doesn't have a charge. Oxygen doesn't have a charge. When you form molecules, you don't think of positive and negative coming together. But what you can think of is making sure that when they share electrons in such a way that they satisfy something called the octet rule. And the octet rule is nothing more than the atoms in the individual molecule, the atoms within a molecule having the same number of electrons, either through transfer or sharing as a noble gas. Here's another summary of the periodic table. Let me change slides and go to our next topic. Okay. And that would be 10.01 Lewis structure. So Lewis structure was, again, this is a concept. It's not really a discovery, but G.N. Lewis is given credit because he was the one that devised this idea that we can represent atoms in a molecule through the valence electrons. And the reason why we can do that is because sorry about that. It seems that my oh no. Okay. I knew I was having issues. My iPad battery ran out, and it's a somewhat old iPad. It's about 4 years old, and so I think I need to replace the battery. But so if I don't charge it overnight, which I forgot to do, it tends to die out on me, which is the case here. So let me go ahead and bring out the PowerPoint on my computer and then use that. I apologize for that. What a bummer. That means I'm limited to my fingers in terms of writing, which is not very aesthetic. So let me go ahead and share my screen with what I have here in terms of my computer. Okay, so here's the PowerPoint from my computer. And let me see if I can't charge my iPad. G.N. Lewis was the guy who gave us this concept of Lewis structure. Okay, and let me go ahead and do this. So let me summarize again what we already know. We talk about the atoms. They're the building block. They're the Lego pieces that makes everything around us. When the atoms come together, it's the valence electrons that are responsible for the chemistry, because the valence electrons are the parts of the atoms that extend the furthest out. And so when atoms collide, it's the valence electrons that mingle with each other. What will happen is that the electrons are either going to be transferred from one atom to the other. And when you have electron transfer right here, what you have is, let's see if I can get my pen. Okay, let's make it red. What you have right here is ionic compounds. When one atom gives up an electron and another atom gains electrons, you form ions, and the ions are attracted. Sometimes the atoms that are involved are nonmetals. When you have nonmetals involved, like carbon dioxide, okay, or nitrogen dioxide, then no one atom is going to try and gain an electron, or no one atom is going to want to lose the electron, because they both want to gain electrons to have the same number of electrons as a noble gas. So since they both want to gain electrons, remember these are nonmetals, it ends up doing neither. What happens is that you have the sharing of electrons right here. Okay, when you have sharing of electrons, then you have covalent molecules. Sometimes the attraction for electrons are not equal, and so one atom has a higher attraction for the electron. We call this attraction for electron electronegativity. Electronegativity is defined as the attraction for bonded electrons. If one atom has a greater electron affinity than the other, then it's not going to be equally sharing those electrons. So this is the case where we have polar covalent. So these are the three types of chemicals that we have: complete electron transfer, electron sharing, or unequal electron sharing. So let me go ahead and go on to the next one. The octet rule is defined in terms of what we just talked about. Atoms will give up, gain, or share electrons so that they have the same number of electrons as a noble gas, 8 generally in the valence shell, 2 in the s orbital, 6 in the p orbital, and that's a total of 8. Transition metals and third row elements. Third row elements are elements below nitrogen, like phosphorus, below oxygen, like sulfur, below carbon, like silicon, because when you get to the third row, you actually have 3s, 3p, and remember in the third shell, you also have a 3d. Now the 3d orbitals aren't filled yet until you get past the fourth shell, but it's still found in the third shell. And because you have the third shell where you have d orbitals, you can accommodate more than 8. So there are some exceptions to the octet rule. Remember, I told you in class, we have these rules in chemistry, and you want to remember them, but there are so many exceptions. The key is to remember these exceptions, because that's the details in the writing. Other elements will not lose so many. Boron will not form B plus 3. Remember, boron has a 3 electrons in its valence shell. The reason why you can't do that is because as you start to lose electrons, then the atomic radius gets smaller because you have more protons than electrons now, and it's going to be more difficult removing those electrons. So B plus 3 doesn't happen because it's not stable. Okay, and then for carbon, you generally don't lose 4 electrons. You start sharing those electrons. Okay, you start sharing those electrons. So here are the Lewis dot structure for the atoms. And what we are doing now is just drawing one dot. Sometimes instead of dots, I've seen, like I do this all the time. Instead of dot, I write X. Okay, so like for carbon, I would write small x. Oops, sorry. I'd write small x to represent the 4 electrons on a carbon atom. And the reason why I write small x is because I want to distinguish the electrons from the carbon, say from the electrons from an oxygen. So I would put a dot or small circles on an oxygen atom, and I would put small x on the other atoms, the other electrons for the other atoms. That way you can see where those electrons are coming from. Anyway, what you have here is the, sure that the chat session is working. You guys have questions on that, please let me know. As you go across the periodic table, the valence electrons increase, and that's exactly what you see. Nitrogen is in the 5A family, 5 valence electrons. Oxygen in the 6A family, 6 valence electrons. And then we look at the trends. Halogen, because it's got 7 valence electron, they often form one bond because they need another electron from another atom. And when these electrons are shared right here, then that represents one bond. So the hydrogen and halogens often form one bond. Later on, you will see that bromine and chlorine, because they're in the 3rd and 4th period, can actually form more than one bond, but that's for Chem 200 chemistry to explain. The chalcogens, that's the oxygen family, they have 6 valence electrons. 2 of these are unpaired. Guess what? They often form 2 bonds. Okay. Nitrogen has 5 valence electrons. They often form 3 bonds. And then carbon, always 4 bonds. If you take organic chemistry, that's a cardinal rule. If you draw a structure in which carbon has less than 4 bonds, that structure is incorrect. There's a few exceptions. Carbon monoxide is a chemical that has 3 bonds, not 4, but it certainly has and obeys the octet. Remember that a 1 bond equals 2 electrons. Okay, 1 bond equals 2 electrons. These are 2 electrons, one coming from carbon, one coming from oxygen. These are 2 electrons. These are 2 electrons. Remember that carbon has 4. So one of these, let me see if I can't change my color. So these are the 4 electrons from the carbon, and these are the 8 electrons, sorry, not 8, 6 electrons from the oxygen. So one of these bonds are coming entirely from the oxygen. We have 1, 2, 3, 4, 5, 6 right here for oxygen, 1, 2, 3, 4 for carbon. So this carbon monoxide is one of those exceptions for carbon always having 4 bonds. Okay, so let's move on. rules of the game. Octet rule works mostly for the second period. If you have an element in the second period, it almost always obeys the octet rule. Okay, hydrogen prefers only 2 electrons, not 8. It doesn't obey the octet rule. It obeys what we call the duet rule. Duet meaning 2. Carbon, 4 unpaired electrons, 4 bonds. Nitrogen, 3 unpaired electrons, generally 3 bonds. Oxygen, 2 unpaired electrons, generally, I always say generally there because there are exceptions, 2 bonds. Fluorine and the halogens, 1 unpaired electron, generally 1 bond. Okay. So if you take a look at this, this is where we are going. We are going towards this guys right here. These are the Lewis structure. Lewis structure. Okay, Lewis structure. And Lewis structure is just the way we represent the molecules based on their valence electron combination. And we always represent pair of electrons between 2 atoms as a bond, and it represents 2 electrons. So this represents 2 electrons, these represents 2 electrons apiece for a total of 2, 4, 6 electrons. Okay, so that's what we're doing. Let's take a look at this table in more detail. HF is the chemical. Hydrogen has 1 valence electron. Fluorine has 7 valence electron for a total valence electrons. That's TVE, total valence electron, as 8. Okay, 7 plus 1. The structure is that there's a bond between HF. Now we're going to fill the valence electrons for the rest. There's 6 remaining electrons. We put that on fluorine because fluorine needs to satisfy the octet. There's 2 here. There's 2 here. There's 2 here. There's 2 here. That's a total of 8. Hydrogen is satisfied with a duet, and those shared electron between the fluorine and the hydrogen is also counted on the hydrogen side. So that's basically 2. Let's go to a more complicated chemical, NO+. Nitrogen comes in with 5, oxygen comes in with 6, but then there's a plus here. Plus means that there is 1 less electron, so we have to subtract -1 from that pool of electrons. Normally, NO would have 11, but because it's plus, it means that it's 1 less electron for a total of 10. The nitrogen and the oxygen also bond with each other. There's a total of, see, this is 1 bond, this is 2 electrons. So if we take the 10 electrons that we know is from the total valence electron, and we subtract the number of electrons in the bonding, the remaining electrons are called the lone pairs. 8. So if we take 8 divided by 2, that equals 4 lone pairs. And so what we see here is, this is not good. Okay, it just tells you that I'm jumping ahead of myself. Let me erase that because this doesn't tell me that it's 4 lone pairs. It only tells me that the there was 8 remaining electrons to satisfy the octet. So this is the octet right here. Each atom obeys the octet rule. So forget for now the fact that I was trying to explain to you lone pairs. We're going to see that in more details when I introduce to you something called the bond table. Okay, the bond table. Here's where we are going with Lewis structure. This is formaldehyde, difluoromethane, and nitroglycerin. Nitroglycerin is the same chemical that is used as an explosive, but it's also good in terms of helping stabilize the heart. These are the Lewis structure. Look at the ball and stick model. Look at the Lewis structure. The Lewis structure shows how these atoms are connected, how the bonds are fit between each atoms, which atoms are connected, and then it shows you the lone pairs. These are called lone pairs right here. For each atom, so that the octet rule is satisfied. Here, carbon doesn't have any lone pairs. Here, carbon doesn't have any lone pairs because it already has 8. This carbon doesn't have lone pairs because it already has 8. 2, 4, 6, 8. You count a bond as 2. This fluorine, however, has 3 lone pairs. 1, 2, 3. That represents 6, and then the shared electrons between the fluorine and the carbon represents the other 2. That's a total of 8. Remember, the underlining principle of Lewis structure is the octet rule. So if you want to do the Lewis structure, you can do it by inspection if the chemical is easy enough to analyze. First of all, you guys need to know how the atoms are arranged. That's the atomic sequence. For carbon dioxide, carbon is in the center and the oxygen flanks the carbon. Then what we do is we put in the valence electrons for each of the atom. Oxygen has 6, carbon has 4. These are the Lewis dot symbols for the elements. Then what we do is electron gymnastics, where we figure out how to rearrange these electrons so that each atom can have 8 around it, applying the octet rule. And if you do that, you come up with this type of architect, and finally you get this type of structure. Remember, 2 electrons that are shared between 2 atoms represent a bond. So what we have is 2 bonds between each carbon and oxygen. Carbon will have 4 bonds on 2 in each side, and then oxygen, to satisfy the octet rule, has 2 lone pairs. But if you had to do everything from inspection, then it would be very complicated because it's basically a hit and miss thing in terms of doing Lewis dot structure by inspection. And maybe your book shows you that. I have a better proven method that always works, but you have to buy in to the way I'm teaching it to you, okay? I've found these techniques through different textbook, and it's called the bond table. And you'll see why it works because of the formula that we use. First of all, Lewis structure by bond determination. That is, you first need to figure out how many bonds in the structure. And then if you can figure out how many bonds in the structure, then you know how many electrons from the total valence electrons to commit to the bonds. The remaining electrons are your lone pairs. So first you need to know the atomic connectivity. Generally, when you're given the formula, the first element in the formula is the central atom, okay? The first element in the formula is the central atom, except when that element in that formula is hydrogen and fluorine. And the reason why hydrogen and fluorine can never be central is because central atoms, A, needs to have more than one bond. More than one bond requires a minimum of 4 electrons, 2 here and 2 here. Hydrogen and fluorine can never have 4 electrons that are committed to bonding, especially hydrogen, so they can never be central, okay? Then what you need to do is you need to determine, once you have the connectivity, you need to figure out how many bonds. And the way you do that is you come up with how many theoretical electrons are required so that each atom has an octet, hydrogen has a duet, and then you also need to count the total valence electrons, okay? That's how you determine the number of bonds. And then the remaining electrons that aren't committed to bonding are your lone pairs. And if you divide the remaining electrons by 2, that is equal to the number of lone pairs. So again, this is a formula that I have for you guys to work out. It's not difficult if you practice it. So keep that in mind. That's why we have a lab later on I think it's experiment 9 where you practice this. But if you do this bond table the way I showed you, you're going to get through that activity very fast. Okay, complete the Lewis structure by drawing the atomic connectivity, show the bonds, and then complete it by putting the lone pair electrons. That's how you do this technique. So let me show you how to work on this technique. First of all, generate a table like this. It's like a multiplication table. At the very top left corner, you write the formula. Okay, we're doing a simple one, carbon dioxide, to show you that using the bond table, we get the same answer as what we just did previously. You break it down by the atoms. Carbon, there's one carbon. Oxygen, there are two oxygen, and then this species has no charge. So you don't add an extra electron, you don't remove an extra electron. If this was -2, you would remove two electrons. Sorry, if it was -2, you would add 2 electrons to the total. Anyway, that's the first thing that you want to do. You want to write the formula, then you want to itemize the different atoms. 1 carbon, 2 oxygen in this case, and this is neutral. So the first thing we're going to do is determine the octet electrons. The octet electrons is very simple, okay? Don't make this harder than it is. It's either 8 or 2. And the only reason why it's 2 is because the atom in question, I apologize for my writing, is hydrogen. Because hydrogen, in order to satisfy in order to give it the same number of electrons as the closest noble gas, is satisfied with 2. All other elements want 8. Okay, so this column can only be 8 or 2. Don't make it harder than it is. 8 or 2. For carbon, we say 1 times 8. For oxygen, we say 2 times 8. Now, what does this mean? It means that if we were in utopia and all the atoms are satisfied, they're satisfying the octet rule, how many total electrons do you need? Well, you need 8 for carbon, you need 16 for the 2 oxygen. Okay, this is the ideal setting, octet electrons. If we add that up, that's 24. Now we have to go to reality. The reality is total valence electron. How many in reality does the carbon atom have? It has 4. How many in reality does the oxygen atom have? It has 6, but there are 2 oxygens, so that's 12. If you add that all up, that's 16. The magical thing about these 2 numbers right here is that if you subtract it, by the way, this is the atomic sequence, carbon in the center, oxygen flanking. If you subtract those 2 values, the octet electron and the total valence electron, those are the number of electrons you have to commit to bonds. And remember, it takes 2 electrons to form 1 bond. That's why you divide by 2. So if you do this, you know exactly how many bonds in this structure you have. You have 4 bonds. And the way to draw 4 bonds is just connect them. 1, 2, 3, 4. That's 4 bonds, and they have to be evenly distributed. Okay? Now remember that in our 4 bonds, we use 8 electrons. We had a total of 16. We have a total of 16 in this structure. 4 from carbon, 12 from the oxygens, but we've already used 8 in the bonding. That means that we have 8 remaining electrons. Those 8 remaining electrons that we haven't accounted for yet are going to be our lone pairs. Okay, so 16 minus 8 equals 8 remaining electrons. 8 divided by 2 is 4 lone pairs. And so here they are. What we need to do now is we need to look at the other atoms here that do not satisfy the octet. Carbon satisfies the octet. Oxygen does not. It already has 4. It needs 4 more. So from our 4 lone pairs, we've used 2 on this oxygen and then 2 on this oxygen. For this structure right here, that's our Lewis structure. This little trick called the bond table always works, because even if you don't have the structure, you already know how many bonds and how many lone pairs you have in that chemical. The bond table gives you that information. But more importantly, it gives you an advantage because now you have something concrete to work with. Let's look at a more complicated example. Let's look at SO2. SO2, sulfur is in the center. Remember, that's the same first atom in the molecule, and then oxygen flanks it. And you might think, oh, SO2 should be the same as CO2. Okay, it should be like this because we already did CO2, but you're going to be wrong. And the reason why you're wrong is because carbon and sulfur are not in the same family. So this is the wrong structure. Don't jump ahead. Work it out from the fundamentals. And the fundamentals are this way. Sulfur dioxide, 1 sulfur, 2 oxygen. Octet, 8 for sulfur, 2 times 8 for oxygen. Okay, that's a total of 24. Reality, 6 for sulfur, 2 times 6 for oxygen, that's a total of 18. We look at the sequence. We know that 24 minus 18 divided by 2 is 3 bonds. So this guy actually don't have 4 bonds, it has 3. So the way we do 3 is we put a bond to 1 sulfur and oxygen, we put a second bond here, and then we put our third bond. We're limited to 3 bonds. Don't draw 2, don't draw 4. You're limited to 3 bonds. In our 3 bonds, we've used up 6 electrons. So that's a total of 12 remaining electrons that we haven't accounted for. Guess what? We're going to have 6 lone pairs. 6 lone pairs. Because if we take 12 divided by 2, that's our lone pair structure. So here's our 3 bonds. Here's our calculations for our lone pairs. And let's go over here. I don't want to show you the structure yet. This always work the flanking atoms first. That is the outer atoms. And then when you have extra electrons, look at the central atom. This oxygen only has 2. We need to give it 8, so it needs 6 more. That's 3 lone pairs. So we've used 3 lone pairs in this structure right here. We've got 3 lone pairs to take into account for a total of 6 electrons. This oxygen already has 4. It needs 2 more lone pairs, 4 more electrons. So we have to subtract 2 from this. Okay, so what we have is 1 lone pair, and guess what? That lone pair goes on the sulfur. Now, if you look closely, you will see that this oxygen has 8, this oxygen has 8, and this sulfur right here has, see if I can't change pen color. It has a total of 8. The octet rows of 8. And that's what we see right here. Okay, that's what we see right here. That is the Lewis structure. But even if you didn't draw the Lewis structure, you already know it's got 3 bonds, 1, 2, 3, and it's got 6 lone pairs, 1, 2, 3, 4, 5, 6. Because in my Canvas questions, what I generally will do is I'll just give you a formula and I'll ask you to calculate how many bonds does this chemical have, how many lone pairs does it have. Okay, so not even drawing the structure, you guys can already calculate this based on this bond table. Let me go ahead and show you more complex example. This right here is ClO4. Remember, this guy has a negative charge. So we're going to account for the chlorines, the oxygen, and the fact that it has an extra charge here means that we have to add 1 more electron. We have to add 1 more, but not in the octet. Octet is 4 for chlorine, sorry, 8 for chlorine, 8 for the 4 oxygen, that's a total of 32. We have to account for 40 electrons in an ideal world. That's what octet electron means. Remember, this column can only be 8 or 2, and only 2 for hydrogen. Reality tells us that chlorine has 7, oxygen has 6 apiece, and then this comes from the fact that this is a -1 charge. If it was a +1, then we would subtract 1 electron. The fact that it's -1 means that it has 1 added electron. And that extra electron is important because we need an even number of electrons. If we ever have an odd number of electrons, it's violating the octet rule automatically. Now that we have that, let's count the number of bonds in this guy. And 40 minus 32 divided by 2, that's 4 bonds. So we do 4 bonds by drawing 4 lines. The next thing you want to do is calculate the number of lone pair electrons. So 32 minus 8. Why 8? Because 8 is the number of electrons we already committed to bonds. 32 minus 8 is 24. 24 divided by 2 is 12. So that's a total of 12 lone pairs. And you can see right away that each of these oxygen will have a total of 6 electrons, or 3 lone pairs. 3 lone pairs times 4 is a total of 12 lone pairs. It works in terms of the Lewis structure. It works. And notice I'm not guessing as to where these electrons originate from. I'm not looking at, okay, I have 7 electrons from chlorine. How do they go? What I do is I take all the electrons, I just put it in a pool, and then I redistribute those electrons in such a way that it obeys, that it follows the octet rule. We put a bracket to indicate that the whole thing is -1 charge. Here's another example, PO3 -3. Notice it's a -3, so we have to add 3 more electrons. Here's our formula. Here's our atoms and charge. Remember that phosphorus is in the center. Oxygen flanks the phosphorus. Let's calculate our octet electron. That's a total of 32. Let's calculate the total valence electrons. Phosphorus comes in with 5. Oxygen comes in with 6 apiece times 3. That's 18. And then the 3 comes from the fact that this is a -3 charge. The -3 tells you that there are 3 extra electrons. If we add this all up, it's 26. 32 minus 26 is 6 divided by 2. That's 3 bonds. Okay, 3 bonds. If you take 26 minus 6, why 6? Because those are the number of electrons we commit to the bonds. Okay, those are the number of electrons we commit to bonds. That's 20. 20 divided by 2, there's going to be a total of 10 lone pairs. So let's complete the octet. That's 1 lone pair, that's 2 lone pair, that's 3 lone pair. You're going to put 3 lone pairs here. You're going to put 3 lone pairs here. That's a total of 9. Remember that we have 10. We have 10. 20 divided by 2 equals 10. But we've only used 9. Where does the 10th one go? It goes on that phosphorus. That right there is the Lewis structure of the phosphite ion. Phosphite ion. See how easy that is? Once you get the hang of it, it goes fast. You don't have to guess where the electrons are going. That's why I like to teach Lewis structure via the bond table, because once you get going with this concept, this organization, it's so much easier than guessing. Let's look at a more complicated chemical. The dihydrogen phosphite chemical. So again, there's going to be a total of 6 elements here. It's got a -1 charge, so we have to add 1 more electron to the total valence electron. Here you can see the sequence. The phosphorus is the center, flanked by the oxygen, and then the hydrogens are attached to 2 of these oxygens. You don't know that, so I'm going to have to give you that hint if I give you a question concerning this. Okay, I need to show you the atomic connectivity, and then it's up to you to put the electrons in place so that each obeys the octet rule or hydrogen, in this case, obeying the duet rule. So let's look at octet. 8 times 1 for phosphorus, 3 times 8 for oxygen, but notice it's 2 for hydrogen. 2 for hydrogen, because hydrogen cannot get 8, it can only do 2. It's called the duet rule. So that's a total of 4 here, 2 times 4. If we add that all up, we get 36. If we were in an ideal world, if we have 36 electrons, all of these atoms would have an octet, hydrogen would have a duet. But we are not in an ideal world. We are in reality, which is total valence electrons. And so let's count. Phosphorus comes in with 5. Oxygen comes in with 6 apiece. Hydrogen comes in with 1, but there's 2 of them. And then there's a negative charge. Counting these electrons is so critical, because if you miscount, you're going to be thrown in the wrong direction. So always double check this bond table, because if you put 8 here instead of 2, you're not even going to get to the correct answer. Okay, it's important that you follow the rules that I give you. This is a total of 26. 36 minus 26, that's a total of 10 electrons committed to bonding, 5 bonds. How do we do 5 bonds? Start with connecting these guys. That's 3, that's 4, that's 5. Okay, we've used 10 electrons in the bonding. That leaves 16 remaining. That gives us 8 lone pairs. Well, 8 lone pairs, 16 divided by 2, okay, 16 divided by 2 is 8. Let's do our 8 lone pairs. We know that oxygen doesn't have an octet. Always work the flanking atoms first. Now it has 8. There's 3 there. Here, it's already got 4. So we need to put 2 lone pairs. That's a total of 5 lone pairs. Here, it's already got 4. We need to put 4 more, or 2 lone pairs. So what I've used so far is 1, 2, 3, 4, 5, 7 lone pairs. Minus 7 lone pairs that we have so far. We need to have 1 more lone pair to account for. That lone pair is on the phosphorus, because phosphorus only has 6 shown. That's the Lewis structure for H2PO3 minus. And you see that in this sequence right here. Okay, bond table is where it's at. So here are more examples of different compounds that you guys should be able to do. These are the Lewis structure. Okay. Then the next chapter, we're going to determine the geometry for this chemical. What is the geometry? And the geometry will either be linear, bent, trigonal, tetrahedral, pyramidal, or bent tetrahedral. But that's not until next week, okay, in terms of the geometry. Now, there are exceptions to the octet rule. Let me review them. If you have an odd number of electrons, if you count your total valence electrons and it's an odd number, automatically it's not going to obey the octet rule. Okay, like NO. This is a neutral chemical. You're going to have 5 from nitrogen, 6 from oxygen. 6 plus 5 is 11. There's no way getting around it. It's an exception to the octet rule. If you have an electron deficit, because you can't remove all the valence electrons, especially for boron and beryllium, you have an exception. Boron is going to be satisfied with 6 electrons in its valence shell. Beryllium generally will be satisfied with just 4 electrons in its valence shell. It's an exception. Valence shell expansion, that's when you have elements in the 3rd period or lower, because now they can use their d orbitals like that. Phosphorus pentafluoride. Notice that there are 2, 4, 6, 8, 10 electrons in the valence shell of phosphorus. It's an exception to the octet rule. Okay, so valence shell expansion, you're going to have to modify that bond table. This is the modification. I don't think you guys need to worry about it in chemistry 152, but you will worry about it in chemistry 200. I might talk about this next time, but I can see that we're running out of time. So I just want to wrap up this particular discussion, tell you the summary. If you're going to do Lewis structure, and it's the chemical is complicated enough that you can't do it by inspection, then please practice the bond table approach, because the bond table approach will always tell you how many bonds in the structure, how many lone pairs in the structure. You need to figure out what the connectivity sequence are. Remember that hydrogen and fluorine can never be central, but once you understand the connectivity sequence, then you can fill in the number of bonds and then fill in the number of lone pairs so that each atom satisfies the octet rule if it's not an octet rule violator. Remember that hydrogen satisfy the duet rule. So that pretty much takes care of that section. And what we're going to be doing next time is using the Lewis structure to determine molecular geometry. Okay, so let me look at the chat room and see what, when do you give the correct answer for the midterm? Well, the midterm solution should be released as of yesterday. So I'll double check to make sure that the solutions are released. What you do is you go to your grade book, look at the score that you got on the midterm, click on that score. It'll take you to your work, and then you will see whether or not you've got a question incorrect or correct. Okay, so I'll double check that after today's session. For those of you in lab, we're going to start lab at 3:15, and I'm just going to walk you through what you guys are going to be doing. So meet me on the other side in the lab Canvas course for lab at 3:15. Let me just see. So yeah, it'll be released. If I can't do it right after class right now, I'll do it after lab. Is hydrogen and fluorine the only exception? No, I didn't say that fluorine was an exception. I said that fluorine can only have one bond. Fluorine is satisfied with 8. Only hydrogen is the exception. Hydrogen simply wants 2, not fluorine. Fluorine wants 1 bond just like hydrogen, but it needs 8 electrons in its outermost shell.